You don't know the number. My -3 eyesight is really having a hard time.
One class for every semester and kid.
Sure.
I think it's less broken.
Okay, let's get started here today. So I said I was going to post some papers after the last lecture, and I didn't. And I said I was going to give you a quiz, but obviously I'm not because I didn't post the papers. So I posted them on Piazza like 10 minutes ago, particularly the cuDNN paper. Please do take a look at that. It's less of an academic paper. It's an archive post, but it really talks about this optimized library that NVIDIA has released for these machine learning computations, okay, for deep neural networks. That's what cuDNN is supposed to be. Like the BLAS for deep neural nets, essentially. And so they go through some techniques in there that it'd be good to understand. Once you guys have read that, I'm going to jump back into machine learning acceleration a little bit. But for today, we're going to move on to the GPU architecture side of this class. Okay, so everything so far has been CUDA, has been programming, and then we had this sort of brief segue into machine learning workloads, because obviously those are super important, but still it's from the program, not much on the architecture. So today we're going to move into the architecture of GPUs. And so the material here is, the reference book is this book that, I wrote with co-authors back in 2017 or something. I think we released it in 18. So, I think it's free. People have said it's free. You can look at it for reference, but I'm not going to test you on anything from the book. It's going to be mostly just what we go through in the slides. It's just there for additional context. There's also a simulator and a simulation manual that really closely follows a lot of this architecture. So if you took 565, the simulator you used was what?
Gem
5, right? Who loves Gem 5? Nobody. Okay. I know. Does anyone know who Jason Low Power is?
Funniest name I've had.
Yeah. So he's the guy who nominally develops Gem 5. He's sort of the one who got. So Gem 5 was this. It's a simulator that was a combination of the M5 simulator from Michigan and GEMS from University of Wisconsin. And they sort of bolted these two things together to create this out-of-order multi-core simulator that is now this giant piece that is Gem 5. And the graduate student who sort of took over that project, his name was Jason Power, and I actually interned with him back when he was a grad student. He's at UC Davis now as a professor, and they got married. And his wife's name was Lowe, and instead of her taking his name, they concatenated the names to Low Power. That's why his name is Low Power, because they're both nerds and they thought that would be awesome. And obviously that's clearly really cool for him because he's an architect, even though he doesn't do low power research, but literally his name. So anyway, I know Jason quite well. He runs Gem 5 boot camp. Maybe some of you have seen advertised. And yeah, he'd be super sad if I told him that I asked you guys if you like Gem 5 and no one said yes. It is what it is, right? It does a lot of things. It is complicated to figure out, especially from a software engineering perspective, especially for people who are used to Verilog and not used to C++, which is most of our students. If you ask people in computer science, they'd probably be more comfortable with Gem 5 than they would be with 437. But based on the students that we usually get in ECE, the software complexity of Gem 5 tends to be a steep learning curve. So you can't use, well, you can actually. Gem 5 has a GPU extension now. It's just not very good. But generally, you can't use it to do CUDA. Okay, you can use it to do AMD or OpenCL based simulations. But if you wanted to simulate GPUs, there's a couple of CUDA simulators out there. The only one that's really actively maintained is this AccelSim GPU sim combination, and that's my group sort of actively maintains this thing. There's a manual that is sort of dated now for an older version of the thing. If you look at the GitHub repos for this, and I'll post this on Piazza, hopefully today, today, let's say, there's some good README documentation on how all this is put together. I also made some YouTube videos during COVID for this class, actually, that then now have like several thousand views because apparently people found out about them and like watch them when they try and learn how to use the simulator. So I'll point you at those two. So the point of this whole spiel is that when we move into the next part of the class, it's hardware simulation. You're going to have to use a simulator. We're going to use the Excel Sim / GPGPU Sim simulator. Okay. And what I'm teaching you here is modeled inside that simulator. Okay, just like how Gem 5 loosely models an out-of-order multi-core with cache coherence, etc. The GPU simulator models the sort of microarchitecture and system design of a GPU, and you can run CUDA programs on it. You can launch a CUDA binary. If you set things up right, it will simulate that CUDA binary in the GPU, tell you how many cycles it took, tell you what your cache misses were, give you all those sort of rich statistics that you'd expect from a simulator. Yes, question? Will it run on a GPU? Unfortunately, no. CUDA programming is hard. It's hard. So it's actually there's two threads. Okay, there's two threads. One thread runs the CPU code. The other thread runs the GPU simulation. It's hard to parallelize a simulator. Even Gem 5 is one thread, right? You know how hard parallel programming is. Now imagine trying to parallel program, a CPU system. It's very difficult. And then the other problem is you have to basically synchronize on memory, right? Even if you parallelize, like let's say that you put every core as a thread, right? In a CPU or a GPU, whenever they have to go touch memory, you need to synchronize them. So now any benefit you get from speed and parallelization gets smashed down by the serialization of going to the memory system. And it makes the code way more difficult to program if you went multi-threaded. Conceptually, it's a lot easier to think about things from a single thread perspective, especially for people who aren't great software engineers, like most architects are, right? We don't want to force people to learn how to do parallel programming to model architectures. So it doesn't run on a GPU, and in fact, it runs on one CPU thread. So the downside of this is that it's much, much slower than Silicon, right? Gem 5 is also much, much slower than Silicon. Simulators typically are slowdowns on the order like 6 or 7 to 8 orders of magnitude slower than Silicon, which, you can't get around that, right? Yeah, Silicon is like transistors operating at 4 gigahertz. You're trying to simulate what happens on that cycle with x86 instructions in a single thread. Like, it's going to be fantastically slower no matter what you do. But you get the ability to sort of look at things in like a really fine-grained level of detail. You can make all kinds of simplifying assumptions, like make some things perfect and see what happens. And so that's kind of the point of a simulator, is you can stretch and move things in directions easily to do limit studies and look at more complex architectures than you could if you have to write RTL, which is going to be way harder in general to model like strange things. Okay. Does that answer your question? So no, it does not run on a GPU. It's a single threaded CPU simulator. Okay. Other questions so far? So yeah. And this is part of your assignment. So the next assignment is going to be modeling stuff in hardware, and you're going to use this simulation infrastructure to do it. We have some, I think, fairly robust documentation to get you started and make sure you can complete the assignment. And then sort of the bonus part of this assignment is more like a project, like you would have in 565 or 666, where you go off and either implement a paper or think like, oh, there's this cool idea I want to try out. And you can do that as the last part of this assignment. Okay. And so I think it's in 4 parts. The first 3 parts are sort of more hand-holdy, like, hey, like go mess with the thread block scheduler, find the code for that, change the way it operates, do some plots, do some analysis. And then the last part is if you want to go off and sort of do something more open-ended, go right ahead and we'll mark it as a bonus. Okay. Has that been released yet on Brightspace? So it probably won't get released until we move into the phase 3 of the class. I think I'm just going to go ahead and release all of the material on Brightspace, because even some of the number 4, because we've already gone through some of the stuff that was traditionally in the 4th section from the ML stuff. So I'll probably work with the Brightspace people to just release everything and then give you some kind of mapping. Who's watching the videos on Brightspace that shows up at this class? So like a couple of folks maybe. Okay, so all right, so people do watch them. Obviously the online people do more exclusively, but okay, some of you guys do too. All right, so in a 10,000 foot view, what does a GPU look like? So we looked at these marketing pictures from NVIDIA of, a sort of cartoonish guide shot of what the GPU is. But if we want to model this, at a simulation somehow, we need, a more fine-grained picture of how this looks. So inside the simulation infrastructure, and sort of when we go through, how the architecture is designed, we're going to assume that it starts out with a SIMT core, SIMT, single instruction, multiple thread. That is an SM. Okay, so not like a CUDA core, like NVIDIA calls like every lane a CUDA core, because it's sort of, you get more cores if you count every lane as a core. Really, a GPU, if you're drawing an analogy to a CPU core, this SIMT core, the SM, is the core equivalent. Okay, so SIMT core here is the equivalent of an SM. We call it a SIMT core because because SM is an NVIDIA specific terminology. In AMD, they call it something different. Does anyone know what they call SMs in AMD GPUs? Compute units, CUs. Okay, those are the same thing as an SM. It's basically the highly multi-threaded core. These cores get grouped together in what are known as concentrations or clusters, and then connected to the on-chip interconnect. So there's some interconnection network. Okay, and you could, let me bring out my pencil here. Give me 1 second. Okay, so you've got these cores, these are the SMs, each of these individuals, and then they're sort of grouped together in what we call the SIMT core clusters. NVIDIA, I think, calls this GPCs or something. It's basically like some aggregation of the cores together. And then those cores have one single tap on an interconnection network. Why would I want to do this? Why wouldn't I just give every SMT core its own tap on this interconnection network? What's a reason why I wouldn't want to do that? Yeah.
Because you're probably not, every single core is not accessing the interconnect network and memory at the same time.
Right.
So using this, you can have, let's say you're not going to be using 100% of the GPU. Let's say you're going to be using 50%. You can put each thread in one core cluster and still get the same performance.
So you're saying is that on any given cycle of the interconnect, one core is not going to have one access on every cycle on average.
Right.
So you don't necessarily need to feed the core at the same rate as the interconnect. So that's true. So then if I time slice between multiple cores, then I can keep that one port busy. From a hardware design perspective, what is the downside of having too many taps on this interconnect? Yeah.
Well, just for kind of the space on silicon.
Yeah. So space and energy on silicon, if you're designing an interconnection network, every tap you add to that network, every import port you add to the network, scales the area, scales the energy. This interconnection network is actually a crossbar because of the way these cores are connected, and crossbars, as we add more taps on either side, start to scale as a square, right? And it's expensive. So they want to try to reduce the number of taps on the interconnection network. So they group the SIMT cores of the SMs together, and then they basically all share, one port on the interconnect. And there'll be some round robin arbitration mechanism to say which core will get the interconnect access on any given cycle. And there's some buffers in there because any real system is just filled with buffers everywhere, right? When you cross clock domains, when you're sort of, arbitrating between things in a time slice manner, you need buffers to buffer, stuff that's gonna come across. Okay. So the cores will send requests, which will nominally be global memory requests, okay, out through these interconnects. So loads and stores will come out through the interconnect. And then it's connected on the other side to a set of what we call memory partitions. Each of these memory partitions contains a memory controller, which maps to one memory channel. Okay, so a memory channel is a set of discrete pins coming off of the chip that connect it to the external memory. Okay, which could be GDDR5 if you're talking about a graphics centric chip, HBM2 if you're talking about compute centric, H100s, etc. And then each of these things, we don't just call it a memory controller because it also contains a slice of the L2 cache. So the last level cache there'll be a part of the last level cache inside this memory partition as well as a memory controller. And then there's a mapping function that will spray your address space, your physical address space, across all of these different memory partitions. Okay. So what this does is create a massive, well, relatively massive, highly banked L2. Because every one of these memory partitions contains one bank of your L2. So when you buy a GPU and it says that it has, let's say, 10 megabytes of last level cache, or 20, 40 megabytes of last level cache, that last level cache is actually spread across multiple banks in each of these memory partitions. Okay. Questions on that? Questions so far? All right. So requests will come out from the core. So if I'm doing a load, the load will come out from the core. It will get routed across this interconnect based on which partition it's going to. So this is an any to any connection, right? I can go to any one of these memory partitions because the address space is completely sprayed across all of them. So it's not like one cluster is limited to going to one partition. They can all go to all of the partitions. Because that's the way that the space is, the memory space is divided. So it'll choose which of these to go to based on a physical address mapping. We'll talk a lot more about this when we talk about address mappings in the memory system. It will go in here. There'll be an L2 or a last level cache that it checks to see if it's been loaded on chip yet. If not, then it will go to the dedicated off-chip HBM or DDR5 or DDR7 or whatever, GDDR7 or whatever you have as your external memory source. That will be, then it will sort of satisfy it, come back, fill the L2 cache, then get routed back down to the core if we're doing a load. If it's a store, then it'll send the store out, store it through to the L2 cache, potentially writing back to the HBM depending on your cache configuration, right? If your cache is write back, it may delay the write until it's evicted. If it's write through, it'll send it through to the HBM. That's dependent on what your cache configuration is. And then for stores, they also send store backs back to the cores so you know when the store is complete. Necessary if you really want to maintain any kind of memory model, memory consistency model here, okay? And that's basically it from a 10,000 foot view. Okay, you've got all of these cores clustered together and connected via some interconnect, and you could connect these in any way you like. This could be a ring, this could be a torus, this could be any fancy interconnect you like. It turns out that the thing that works best for this purely bi-directional communication, because there's no core-to-core traffic here. This is not like a CPU where I've got cache-to-cache transfers happening to maintain coherence. I'm only ever going out to my partition and back to the cores. I'm never sending data between the cores because I'm not maintaining any kind of fine-grained cache coherence like a typical CPU does. So that means that your L1 caches are actually incoherent. So if you're accessing data from global memory, you cannot rely on write atomicity in the threads. Okay. This is why programmers are encouraged to use the scratchpad if they have any of that kind of communication, because they can guarantee write atomicity. Questions on this? Yeah, right here.
Wait, so the memory partition is the L2 cache.
So the memory partition contains a slice of the L2 cache or a bank of the L2 cache, equivalent to if you have 10 megabytes of L2 cache and you have 10 memory partitions, then you have 1 meg in each of these partitions. And then it also contains the memory controller.
Okay. Then each then each L1 cache is built somewhere inside the port.
So the L1s are inside here.
Okay.
So there will be L1s inside each of the SIMT cores. In different generations, they've had L1.5s. Okay, because I don't know, they didn't want to call it 2 and make the other one 3. I don't know. So they have additional caches that are sort of centric to each GPC or each cluster. You can build a hierarchy however you like, right? We don't actually model this in the simulator. It doesn't tend to matter all that much, but it is possible to create these sort of hierarchies of varying levels of cache. And modern machines like a Hopper will do this. It has an L1.5 that's shared across the cluster. Yeah.
If it's so distributed, like the L2, would it not cause a big wouldn't there be a lot more misses? Because how does it know which partition to that and hope to find the data?
So the simplest way to do this is modulo. So every 256 bytes of your physical address space is sprayed across each of these partitions. Okay, so 256 bytes lives on partition 0, and then the next 256 bytes of the address space lives on partition 1, and so on and so on and so on. If you have a perfectly evenly distributed access pattern across all groups of 256 bytes, then this works perfectly fine, right? If you have some pathological, like I'm hitting the same page or like I'm hitting the first byte of the same page over and over again, that's on some 4K boundary that does not map well to this sort of modulo type operation, you just emanciate your memory bandwidth. Because now instead of using all of these partitions and all of these L2s and all of these memory channels, you're limited to, in the worst case, one. And you cut your bandwidth by a fraction of whatever that's sort of, we call this bank camping in some instances, or partition camping. It's basically a partition conflict similar to the bank conflicts in the shared memory system, okay? And this mapping, so when we first developed the simulator, we used exactly this modulo mapping. And it works fine for simple workloads. For workloads where there are more pathological strides, it completely does not work. So in reality, the real hardware has complex hashing functions to try to evenly distribute the address space based on, based on observed memory access patterns across all of these partitions. Because this is like, if you do not evenly spray the traffic across these partitions, your memory bandwidth is just dead. And if your memory bandwidth is dead and you have memory bound applications, your performance just crashes. So it's a huge problem. And they have mathematicians inside NVIDIA that try to figure out, based on data access patterns, what the right hashing function should be, because it really is super important. Good question. Other questions here? Yeah.
For the partitions, because they're kind of restricted on how many memory controllers are on the device, right?
Correct.
Is there I know, like the newer GPUs, is there what's the number of partitions, I guess?
So it depends on the generation. I think Volta is 16 partitions. I think Hopper is in the order of 20 something. They tend to scale up generally. Yeah, so it's less than the cores because you'll have, I think a Hopper GPU has 180 SMs or something. And then it'll have on the order of 20 something memory partitions. I can't remember the exact numbers now, but that's sort of the ratio, okay? And it's meant to be balanced, right? In this big system design, you're trying to balance the system. If I have way too many cores versus number of partitions, then, then I'm wasting all that core capacity because I never could feed it the bandwidth it needs, right? So try to balance the system as much as possible in general. So it'll really depend on the rate at which you can get data out of each of these partitions. Good question. Other questions? Yeah.
Why does the interconnect network have to be a crossbar?
It doesn't. It just is. It's well suited to maximize bisection bandwidth because this cannot be the bottleneck. The on-chip interconnect really cannot be the bottleneck, or else you're not using all the memory bandwidth you built into this thing. So it's not area efficient, it's not energy efficient to use a crossbar to do this, but since it is this bidirectional memory traffic, and you really just want to maximize bisection bandwidth, crossbar is sort of the most natural fit if you're willing to pay the area and energy for it. And because it's such a disaster to not have enough bandwidth in this interconnect, it tends to be a crossbar. Okay.
Also, do we have to spray the memory across all the partitions?
You don't have to do anything. As an architect, you can do whatever you want, but that's the most sane way to do this. How else would you do it?
You can have clusters, and you can have the software stack steer.
So like a programmable hash map?
Yeah.
Yeah, you could. Now you have to look up software. This is not virtual to physical mapping, right? You guys know very well virtual to physical mapping, TLBs, page tables. This is lower than that. After I get my physical address, I take the bits of that physical address and then do mappings to partitions, to banks in the memory system, et cetera. Which you probably haven't seen in any other class, but we will look at in this class. Yes, this could be programmable, but it tends to not, it tends to not be. Okay. Other questions? Okay. All right, so that's a 10,000 foot view of this thing. So we're gonna drill into each of these components in detail throughout the next sort of few weeks. We're gonna talk a lot about the way the SIMT core is designed. Then we're gonna talk about how the memory partition looks, and then we'll talk about HBM systems, DRAM systems as well, to give you a sense of, this is the big picture. How are each of these individual components constructed in GPU? Okay, so what we go through in this class is not necessarily gospel, right? It's not, we don't know exactly what companies are doing. They're tight-lipped about this, even more tight-lipped than CPUs, because CPUs have been around so long that there's really only so many things they can do. And they don't tend to change all that much. So they don't really advertise how any of this works. Why do they do this? Well, competitive advantage, fear of being sued by non-practicing entities. So like if I tell you exactly what's inside the microarchitecture, and then I'm some patent troll that just has a patent that does that thing, then you just told me that you violated my patent and I don't have to do anything and I can go sue you, right? So there's no upside for me to tell you what's inside this thing precisely because it just exposes me to lawsuits essentially. And like I told you before, the major vendors have mutually assured destruction. They cannot go after each other because they have enough to go after the other one. But some bozo who's got one patent, who you can't go after for anything because they haven't done anything, just sees that you violated their patent, they can go after you, and then you're in the hole for, you know, X million dollars. I think this is sort of, I don't want to call it bozo, but that's kind of what happened in Wisconsin, right? Like, those of you who know Guri Sohi, he's not a bozo, I love Guri. But, you know, it's sort of, you open yourself up to this threat. And Intel didn't, you know, for those of you who doesn't know the memory dependence prediction story? Everyone knows this, okay? Okay. So there's been like some lawsuits against Intel, and they also sued Apple in the news. Okay, 565, who remembers memory dependence prediction? Okay, most folks. So if I have a load in the store, like register dependencies you can pick up from the ISA, you just know them, but memory dependencies, load stores, you don't know them, right? So you have to predict if the store is going to be the same address as the load because you want to rearrange stuff, okay? And you don't want to violate that. So there's mechanisms to predict this. These folks at Wisconsin, T.M. Vijay Kumar was a graduate student on these patents and these papers when they came out. They basically patented a mechanism to do memory dependence prediction that they proved in court Intel violated. Okay, how? Through reverse engineering, because of course Intel didn't tell them exactly what happened. But University of Wisconsin took them to court and sued them for like, who remembers the amount?
862.
862 million? Is that what it was? Okay. Yeah, so some giant amount, because if you sell a lot of chips, so this is where lawyers make their money, right? It's like, okay, you sold, you know, $200 billion worth of chips. This little mechanism improved your performance by 10%, which we estimate increased your fraction sales by 1%. So like 1% of 2 billion is whatever, right? And then, so you owe me $86 million, right? This is where lawyers argue. And they won. They basically proved that they violated the patent, and Wisconsin won the patent litigation, and they had to pay WARF, that's the name of the Wisconsin, whatever it is, like some kind of patent office at the University of Wisconsin. And I think that as a result now, like, because WARF has been so aggressive in this one and a lot of other cases, like all incoming PhD students are like guaranteed funding or something, because there's just like a pile of money sitting around these various lawsuits that they've gone after. And they went after Apple, right? And I think they won like 200 million or something, because it was also in the iPhone. So they're like, okay, look at all the iPhones you sold, like, give me the money. And then they challenged, and they lost that on appeal. I think there was some issue on appeal that caused them to like be taken back. So this is in the minds of all hardware vendors that, oh crap, like I might be violating somebody's patent who I can't countersue because they haven't done anything for, like, you can't countersue Wisconsin, like for what? Like they didn't produce anything, right? All they have is the patent. And so they don't intentionally tell you what's inside this thing, because then it makes it much easier to sue them. You have to go through the hard work of reverse engineering it and then proving that like this is what they actually did, which is a really hard exercise. So that sort of explains partially that second point, why no one releases precisely what is inside hardware because of legal exposure. And the third point is that it actually takes a lot of work to document things. You guys know, as engineers yourself, like most documentation is crap, right? Even in software, even in hardware, even in industry internally, it's still kind of crap. Why? Well, because like after you got the thing to work, why don't you go build the next thing? Like, why are you going to sit around writing Word docs on how it all works? Like, are you really going to get all the engineers that designed all the microarchitecture to go write 4,000 pages of documentation on it? That sounds like a waste of resources. And you can't hire some English, bachelors to go write that because they don't understand anything about what's happening inside of it. So the only people that could actually write the documentation are people you're better off paying to go do something else than to write the documentation. Okay, so there's all these perverse incentives against people being open source in the hardware industry, much more so than software. Software, there's like this big open source thing and everyone wants to be open source. It's like kumbaya, we all love each other, whatever. Hardware is not like that. Hardware is very closed, very sort of, combative. And I think it's sort of rooted in, patents and, patent exposure in hardware definitely has been a problem. Okay. So anyway, so that's why we don't know precisely what's happening. So how did we figure out any of this? How is any of this valid or modeled? So you can read white papers, right? They do have the white papers. They have these big cartoon drawings of what the high level architecture looks like. They give you some high level details about what's happening. You can take a look at the programming manuals and try and infer what's going on based on what it says inside, for example, the CUDA programming guide or the PTX documentation. You can go look at articles, published in IEEE Micro, et cetera, that describe the architecture at some level. And then you can go dig through patents. You can go say, all right, I don't know how they actually implemented the register file, for example, like that's hard on GPUs. So you go look at patents published by NVIDIA or AMD and you're like, oh, look, they have a patent on this thing called the operand collector. Maybe that's what they did. Let's go measure it and see. And so that's sort of how all of this, the sort of description that I'm going to give you in the next few weeks is derived. We don't know precisely how these machines actually work. We sort of derive it from all of these public sources and then good old fashioned reverse engineering, writing micro benchmarks to try to figure out what's going on inside the cores themselves, and then potentially modeling it in some type of simulation. And, my group does a fair amount of this type of work because you kind of need to if you want to do research and have it be relevant. Any questions on this? All right, so one person learned about the Wisconsin thing, right? Okay, good. Did TM Midgecomer tell you guys about this? Or you just know? How do you all know then?
You brought it up once,
You brought it up once?
and then we kind of dug in a little
Okay,
bit.
all right.
Yeah, word of mouth. So,
What's that?
I don't think it mentions that.
Yeah, okay, yeah,
I think Professor mentioned it once.
I see, okay, yeah. So some fraction of that goes to the university and some fraction of that goes to the people on the patents as well, right? So like there is upside for you patenting, like there's personal upside for researchers to patent things in some cases. Intel also put those guys through pure absolute hell, okay? They did not want to give up $86 million.
862.
862? Okay, I thought it was much more than 86, okay? So, yeah, like, I don't know if that was the final amount. I think it got maybe litigated down.
When you look it up, it says 862.
Okay, which is huge, okay? So you can imagine there were lawyers digging through lab notes, okay? Like walking into RA's workspaces and opening up their workbooks to see like when they had written down the ideas or if they'd taken those ideas from somewhere. It was also kind of messy because Intel was actually funding the researchers who did this for something else when they did it. But depending on the structure of the funding, you may or may not own anything that gets invented by those people. So anyway, this was messy as hell. And they actually flew in like the top, like lawyers are ranked. We actually all learned that lawyers have rankings. Like you can look up like who is the best patent lawyer in the country, right? And so Intel had hired like the #1 patent lawyer in the country. And then Warp had hired the #2 patent lawyer in the country. And so I've talked to people who were at Wisconsin at the time who showed up for the trial because it's kind of interesting, right? You have like these farmers from Wisconsin sitting on the jury trying to decide if Intel violated a memory dependence prediction bug. And then you've got these, super smart lawyers trying to like put this into layman's terms with $1 billion on the line. And then there were also a whole bunch of law students that show up because it turns out this is like Geek Central for law students. Like, oh, #1 is going to go against #2. So there was a whole bunch of lawyers and a whole bunch of architects in the classroom or in the courtroom. And apparently it was super interesting. I really wish that I could have been there for it. But it ended up actually turning on some small phrase in the patent, like the way that they had worded something about, I can't remember the precise details, but it was like one sentence that like turned it so that way Wharf actually won the litigation. Anyway, okay, let's go back to GPUs. We haven't sued anybody over any patent violations yet. So what we're gonna do today is look at the core. Okay, let's start at the beginning. Let's look at the core. All right, so let's start with a pretty simple model for how the core looks. So at the guts of this thing is a SIMD engine. Okay, like I said, everything is going to be some vector operation. So you're going to have a SIMD data path, meaning that you're going to give it one opcode. You're going to give it, register identifiers for one particular register. So like R1 or vector register R1, you can imagine. So I'm going to read from vector 1, read from vector 2, and write to vector 3. That is the core of the data path inside the GPU. Though that big wide data path is going to have to read from a register file. Register file is going to have a lot of bandwidth because there's going to be a lot of lanes in that wide SIMD. And then, these two components really are pretty much identical to a vector engine. Okay, it's just a big wide, vector process or vector core with a vector register file. What makes it SIMT or different from, sort of traditional vector extensions is all of the stuff inside this SIMT front end. Okay, so I'm going to have, conceptually, I'm going to have a bunch of threads being programmed. For all of the threads in a warp, okay, I'm only going to do once this fetch, decode, schedule, and then deal with any branches that happen inside of it. Okay, so I'm going to group together all of the threads into warps of certain sizes. On NVIDIA machines, it's 32 threads at a time. And I'm going to do one instruction fetch that's going to service all 32 of those threads. I'm going to do one instruction decode that services all 32. I'm going to do one schedule that services all 32 of those threads. And then I need to deal with the branches because the branches turn out to be kind of a mess, right? Because in branches, some threads can go one way, some threads can go the other, and that causes problems. So we're going to have to innovate there to make this SIMT front end work. System looks very similar to what we've talked about from perspective of CUDA. So I've told you that there's this shared memory. This is what SBEM is here. This is all in core. There's no one data cache, and there's this thing called the constant cache. Conceptually, these are all potentially different storage spaces inside the core. In practice, sometimes they get split and shared. For example, in modern machines, the shared memory is actually shared with the L1 data cache. Okay, and that's sort of subdivided based on how much shared memory you're using. And then once you miss in this sort of memory subsystem that's on core, you're connected to that on-chip interconnect network, which is nominally this port of this crossbar that sends you out to the memory system. So you've got this SIMT front end that is connected to this SIMD backend. And we're going to do fine-grained multi-threading, which means we're not just going to have one warp active on each of these cores. We're going to have N warps, where N is as many warps as we can pack onto the thing as possible. And this is what determines your occupancy. Okay, so when we talk about occupancy in GPUs, it's basically talking about how many warps you can get scheduled on each core. And we're going to do this interleaving to sort of hide the latency of both the pipeline, right? Because this could be, maybe this is a 10-stage pipeline to get through your SIMD unit. And, I can basically do fine-grained switching between one warp or another to hide latency in those 10 stages. If I have 10 warps, then I can issue one instruction from one warp. And then while that proceeds to the next stage in the pipeline, I can issue another instruction from another warp. And then I never have to have two instructions from the same warp in flight at the same time if I have enough warps and my SIMD path is low enough. Okay. Register values stay resident inside the core. You can do context switching in GPUs. In the early GPUs, there was no support for context switching, meaning dumping all of the state out to memory. Why? Because that's generally a very expensive operation because you usually need to context switch an entire thread block. So that's an entire bunch of shared memory. That's an entire bunch of registers. It tends to be very expensive. AMD GPUs do support this kind of context switching now. It's unclear how much, material benefit it brings, but it is supported, but generally it's avoided. You usually, once you schedule something to the core, you don't dump out all its on-core resources. Because we're not dealing with page faults that are going to go to disk, right? In a CPU, you do a context switch if you've got, a page fault where that the thing is not in your memory. You have to go to a spinning disk. It's going to take many milliseconds so you can dump stuff out. In GPUs, you have the equivalent if you're using the virtual memory system that has to come from the CPU memory, but that's still much faster than coming from disk. So generally, it's not really worth it to do a context switch. Questions on this? Yeah.
So if I'm using entirety of this shared memory, is there's a possibility that my thing can slow down because I'm reducing my error rate?
Yep. Possibly. Usually not the case because if you're using the shared memory well, you're probably getting better locality of the shared memory than you would with just whatever the L1D was giving you. But if, for example, you have two reference streams, one of which can be captured in shared memory and the other of which is going to have to go through the memory system because it's input dependent or something. If you grow the shared memory size to shrink the L1D size, you may, like that second operand that had to go through the L1D may crash. And then you could have these perverse trade-offs where you think it's going to be faster, but it's not because you are shrinking the L1D. Good question. Yeah, that's possible. Other questions? And these texture caches, they're still on all parts because they really just roll one design, right? There's still a texture cache inside an H100, even though it doesn't even have a video output, right? Because I don't want to have to redesign my core, redesign my ISA every time I tape out a new chip of a similar generation. So they sort of, you know, there is potentially a lot of, potentially some wasted hardware in these things for different product lines that don't necessarily use the whole system, okay? All right. Okay, so let's talk about the SIMD data path. So one thing I'll note is that this data path can be smaller than the warp size. The simple way to think about this is that it's always 32 wide, but it doesn't have to be. It could be 8 wide, and then you simply just take 4 beats or cycles of the SIMD path to clear each warp instruction. If it's 8 wide, if it's 16 wide, then you take 2 beats. The precise width of this has changed over generations. So, you know, I think in the beginning it was 8, at Fermi it went to 16, and then for Volta they put it back up to 32. I think that Hopper is also 32 these days. And so, yeah, if you make it smaller, this is a sort of a classic hardware design trade-off. The smaller you make it, the faster you can clock it. But the faster you clock it, generally the less power efficient it is. But the wider you make it, the more area you use. So it's this trade-off between, do I make it small and clock it faster than the rest of the pipeline, or do I make it wide, consume more area and clock it slower? It generally is more energy efficient if you've got the area to make it wider because you don't have to crank the clock to keep the same performance. Research has exploited this fact, right? So, you know, there's been some work. Intel actually proposed some work in the early noughts, I guess. Is that what you call the years that start with 1, the noughts? That like 2013, I think, that tried to exploit the fact that, oh, look, your warp is 32, but your SIMD is only 8, for example. What do you think you might be able to do? What clever trick could you play if you're running GPU code and your warp size is different from your SIMD width? In the normal case, I'm always going to spend, so if I have a 4 wide SIMD, and I have a 32 wide warp, how many clock cycles does it take to clear one instruction? 8. Every time. Independent of what's going on. What trick could you play there? Yes. Pipelining? Pipelining. Yes, it is pipelining already. Okay. But what trick could I play to avoid having to spend 8 cycles every time? Any guesses? Knowing what you know about how GPU programs might work? Put it on multiple SMs. Yes, very complicated. What's one problem with GPU code that we brought up? Yes. If you have branch divergence. What might you be able to do if you have branch divergence in the scenario of 4 wide SIMD and a 32 wide warp? How can I make that go faster than 8 cycles? Yep.
Just not run the threads that are master.
Exactly. If I get lucky and some group of 4 is empty, if I have control flow divergence, let's say half of the warp goes to the if and half goes to the else, I'm only going to do 16 threads. If my SIMD width is 4, then I only really need to beat this 4 times. And then I don't have to beat it the other 4 times because I know that they're all going to do nothing. This adds complexity because normally when, you know, if you build the hardware, it's a lot easier to assume that every instruction is just going to take 8 beats to clear. You'd have to add complexity to say, okay, well, if the lanes are off, I'm only going to do, you know, 4 instead of 8. But it's a potential win, especially if you have regularity in your control flow divergence, like half going one way, half going the other. Okay, good observation. And so they had a paper on this. That was the whole paper. It was an ISCA paper in 2013. Yeah, that's what this is. So ISCA 2013. Intel proposed this, just, and the basic idea is that simple, right? Just basically, if your SIMD width is less than your warp size, just skip the cycles where you wouldn't have done anything useful. This is particularly relevant as your SIMD width gets smaller. So if you wanted to apply this, so Intel did this for a reason, right? They have SIMD units that can be conceptually smaller than the big wide GPU SIMD units, at least in some of their product lines. So this made a bigger difference. And we'll sort of see this theme as we go through these stats on microarchitecture. I'll talk about, how it's built, and then I'll introduce some paper that's tried to exploit something about how it's built based on how GPU programs work. Okay, are there any questions on this? You can read this paper, but this is the whole idea. And it makes more impact as the SIMD width gets smaller, right? So if you have a 4 wide SIMD, you can potentially skip, more because you have a finer granularity of things you can potentially skip, and then you can save time. Yeah.
Will help only if those some threads are not doing anything.
Exactly.
But if they're doing different work, then it's the same thing.
So, right, but remember that they cannot do different work in the same same cycle. Because that would require 2 different opcodes flowing through to the SIMD lanes. So this is always true if you have divergence, unless you've got some, and there's other papers that have proposed, oh, well, what if I could just do 2 opcodes and then have some weird routing network to pick which lanes do which opcodes. But now you're starting to complicate the SIMD hardware, and all the efficiencies you get by going SIMD start to increase and make it more complex. But you're right, they have to be doing, it only makes sense if they're not doing something. And that's generally true, they're not doing something. Okay.
If you know that a particular section of the code will have control for
Yeah.
divergence, can't you increase the warp size for that particular section?
Warp size is fixed. The hardware needs to have a consistent warp size for a whole bunch of reasons. The coalescing granularity needs to be burned into the hardware. The number of beats it takes to do each of these instructions needs to be burned into the hardware. You cannot have this fungible warp size at runtime. Look, again, like I said, you can do anything, but having some variable that an OS sets to say what the warp size would be would significantly complicate the hardware to have your warp size be tunable at that finer granularity. Okay. I say that having published a paper where we kind of did argue for variable warp sizes, but the way that we did it was we said that the minimum warp size was 4. So that the hardware, we paid the cost 4 or 8 of having the potential to go different ways, right? And then we said, well, if they all happen to go the same way, we won't use that extra circuitry and we'll save energy, right? So we ganged together things instead of splitting them apart, sort of. And then as they diverge, we let them split apart. So it's something you could do, but having it be that sort of fine-grained, programmable, there are some downsides to that. Good observation. Okay. Other questions? Okay. Does everyone understand this for the most part? Okay. All right, there's some quiz online. Okay. I don't think I've given you the context for this question yet. But if I have this pipeline, okay, this pipeline where I'm going to tell you that for any warp, I only ever have 1 instruction in flight at a time. Okay, so I'm going to issue an instruction from 1 warp, and then I'm not going to issue another instruction from that warp until that instruction I issued finishes. So then how do I keep the pipeline busy? If I do that, if I say I'm going to issue from warp 0 and I'm not issuing from warp 0 again until that issued instruction is completely done, no matter what it was, even if it was a load that missed in cache, how do I keep the pipeline busy if I have such a system? Go to the next warp. Okay. If you have enough warps, if my maximum memory latency is 400 cycles and I have 400 warps, then my pipeline can be 100% busy. Okay. If I have such a system where I guarantee that only 1 instruction from each warp is going to be in flight each cycle, do I need any dependence checking hardware at all? Register dependence. I'm talking about register dependence specifically. Yes or no? Yeah.
No, because they're incoherent, right?
No, because they're incoherent, because I don't care about the memory dependence aspect, right? I don't actually care about load store ordering, because I'm not going to make any kind of order, because that's out of question. So this question is specifically about register dependencies. Do I need anything in the hardware to make sure register dependencies aren't violated? What do you think?
Should have private.
Registers are private, yep. So the answer is no, right? So it's no. If I know that I am not going to go, I'm going to have an in-order pipeline, and I am not going to go to the next instruction until the last instruction completes, I really don't have to do any dependency checking, because I'm not exploiting in a single thread or a single warp basis any instruction level parallelism. I am exploiting my pipeline parallelism across warps, right? Not within one warp, which means I elide completely the need for any dependence checking with register identifiers, okay? Which simplifies the process of design significantly if I built it this way. There's a name for this type of execution. Does anyone know what it's called? It's called barrel execution, okay? Vector units used to use this in the early days of vector processing, like Cray machines, where you would not ever have two instructions from one vector or one, in our case, a warp in flight, so that way you don't need any memory, you don't need any register dependency checking, because you know that all your registers are going to be satisfied by the time you issue next. If you have enough threading, you can cover it. Okay. So that's what we're calling, at least in the book here, the one loop approximation of a GPU core. Meaning we have one loop, we have one scheduler that's just going to go pick from this. I'm going to pick which warp to fetch from on any given cycle. I'm not going to fetch from that warp again until the instruction I fetched is complete. And then I'm just going to switch between warps to do this, to basically cover the latencies in my pipeline. And so this is what we call one loop, meaning that there's really just one scheduler, and that one scheduler is very constrained in what it can pick from, because if it knows that there's an instruction in flight from a particular warp, it cannot issue another instruction from that warp, else it might violate dependencies. Okay, this is just basically saying exactly what I just said. Questions on this? Yeah. No? Okay. All right. So if we have such a system, let's focus on what's interesting in this system, because the scheduling mechanisms here are trivial, right? You really just, you pick one warp to go, and then you enter that instruction, then you pick another warp. That decision on which one you might pick might have some effect, but there's really only one scheduling decision to be made here. So we're still going to have to deal with branches in such a system. Okay, we're still going to have to figure out how we deal with branches inside the hardware. And so the baseline assumption here is that we're going to use something called a hardware or SIMT stack. Who's heard of this before? Did I mention this earlier in the class, the SIMT stack? Probably not. So let's go back and remind ourselves what's happening inside control flow divergence on the GPU. What I've pictured here is what? What am I showing you? With this little, arrows, and what do you think this is? It's the CFG, the control flow graph. This is something the compiler can extract statically. It basically denotes each of the basic blocks in the program, and then constructs edges between those basic blocks for how the code can flow. Okay, abstract representation of the code, so the compiler can do optimizations and can basically do analysis and whatever. So I'm going to have to execute this control flow graph across an entire warp. And in a simple example here, we're going to assume that it's a 4-thread warp, because it's easier than 32, but all of the ideas hold. And then that warp, every time I execute an instruction in this control flow graph, all 4 threads have to be using one of the PCs. And we're going to assume, for the sake of simplicity, that there's just one PC inside each basic block. Okay, so A is a PC, B is a PC. Of course, that's not really true. There'll be multiple individual instructions in there, but we can just, for simplicity, assume that there's just one. Okay, so I want execute this code, but I want it to be correct, but I also want it to be as efficient as possible. So in the beginning, I start executing, and I'll have a mask. We have a mask that represents how many threads are active in the warp. Very beginning of the program, when we start, for basic block A, or we'll call it PCA, and the active mask is all ones because all threads are doing something, okay? Then we encounter this split in the control flow graph. Why would I split in the control flow graph? A branch. Picture this as an if or an else, okay? The if is going to the B block, else is going to the F block. Let's just assume that. So now I have a split. So I'm gonna keep track of this stack. So inside this stack, I've got a top of stack pointer. That's what this represents. I've got a marker for something called the reconvergence PC. We'll talk about how that works in a second. I've got a marker that says what my next PC is. So I know, what I'm going to execute next. And then I have an entry that says what the active mask is. In the beginning, this is dead simple. It's just the PC and the mask is full. As I start to traverse the control flow graph, some warps or some threads within the warp are going to want to go to B, and some are going to want to go to F. In this trivial example, I've assumed that nobody went to F. Okay, all of the threads are going to go to B, so F was an untraversed path. If that's true, then I can just keep my stack as a single entry because I know there's really only one path that I need to explore here. And I update my PC to be B. So everyone's still happy. Okay, they're sort of marching along together through this control flow graph, and they're still completely converged. Now I encounter another if else, and realistic code looks like this, right? Anytime you have conditionals, anytime you have loops, the control flow graph starts to get messy. Now I have two paths, potentially C or D. Now, in this instance, some of the threads want to go down C and some of the threads want to go down B. So I need to make sure that I satisfy both of these paths, but I can only do one at a time because at any given cycle, I can only have one program counter available. So the way that works with this reconvergence stack, and this is how the baseline of how GPUs really operate. Okay, this isn't like made up. This is what's inside the hardware, at least historically. I had this divergence point. So when I hit that branch, I pushed two new entries onto this hardware stack. Okay, one entry that signified the threads in the middle that are going down the D path. Okay, so that's the second entry on the stack. And then another entry that signified the threads that were going down the C path, which are the two on the ends. So when I execute the branch, there is hardware that evaluates where each thread goes and composes a mask for that warp for who went this way and who went that way. And then it basically says that, that all of the threads, the sort of middle threads, right, the 0, 1, 1, 0, they want to go to D, and the 1, 0, 0, 1, they want to go to C. And so I push these two entries onto the stack. But since at any given time I can only do one path, I can actually only execute from the top of the stack. So this serializes the execution of these two paths through the code. The other thing that you'll notice here is that I'm now using this thing called the reconvergence PC. What do you think this represents? Where they're going to come back together. That's what reconvergence means. This was divergence. I diverged, but I need to know where I put them back together. Because in the limit, if I do not reconverge, as soon as they split, if they never come back together, then they'll go off into the weeds and never return. And normally that's bad because usually if they split, they will come back together and then do the same work if the control flow graph is amenable to this. So you can perform something called immediate post-dominator analysis on control flow graphs that will tell you for any given node, what is the next closest node where all of the threads that are all of the paths that entered a particular node, they have to go to this other node also. Okay. So what that means is if I look at B, the point at which I diverged here, there are multiple post-dominators. Okay, to post-dominate means that it's a node that if I went through this node, I then have to go through this other node. D and C are not post-dominators because I don't necessarily have to go to D or C. I could go to one or the other. E is a post-dominator because no matter whether I went to C or D, I had to go through D. G is also a post-dominator because no matter whether I went through E or G, C or D, I have to go to G. But what we care about most is the immediate post-dominator. Why? Immediate means the closest. Why would I want to care about the immediate post-dominator? Yeah.
That's where the reconvergence happens for sure.
That's the earliest point. Reconvergence definitely happens at both of these places, but the immediate post-dominator, or the one that's very closest to where the divergence happened, that is the one that's going to happen first. And we are generally much better to reconverge earlier than later, because the longer you wait to reconverge, the worse the performance is going to be, because you're going to be executing more of the code with the mask being not fully active. Okay, so this information is actually extracted by the compiler. So for any given branch, it knows where the immediate post-dominator is during compile time phase, and they'll insert special instructions to say that, you know, this is where the post-dominator is going to lie. Okay, so you need the compiler's help to find these immediate post-dominators so you know where to reconverge the warp. Okay, and this example, both of these paths reconverge at E. Questions on this so far? Yeah.
So you have to do C and D serially, right?
Correct.
How do you pick between?
It's arbitrary, right? So there's no right or wrong answer here. Really, you could have pushed, it really just depends on which path you push first. You could have pushed D first, you could have pushed C first. In this case, we pushed D first, so then C became the top of the stack, and it's gonna have first priority. Okay, yeah.
If there's like, say C also diverged and then it reconverged on E, would it continue down and then do C and then do both branches under C and then go to E, or would it go like C, D?
Yeah, good question. So the simplest way to do this is to just continually grow the stack and never go backwards. So if I went down the C path and I had counted another branch, but then split those two again, I'm going to keep going down that path because that's what's going to be on the top of my stack. And the reason for this is that the hardware is a lot simpler. You can build a hardware stack where you push and pop things from it. And, you know, you don't want to have these weird scenarios where you're not going to the top of the stack. Again, crazy research has sort of proposed this kind of thing, but generally it's not worth it. So you will, once you pick the path, that's where you're going until that path ends, and then you're going to come back and do the other side. Good question. Other questions? Now, from a functionality standpoint, it would be equally valid to reorder the stack in this case, if you wanted to do that. But, you know, again, that's complexity and it's not a clear win. Okay, good question. Other questions? Okay. All right, so now we're going to execute C. So the way that the front end fetch system works, right, is it looks at the top of the SIMT stack and it says, what is the next PC for the top of the SIMT stack? That's how it decides what instruction this warp needs to execute next. So it sees that C is the new instruction it wants to execute. It executes the instructions from C, which then, you know, execute like this. So this is the timeline down here of how things are going versus time. And it executed with 50% efficiency because there was just no way to not do that. Okay. Then after, you know, when we do that execution from C, it will then move eventually to the E place, right? Eventually the next PC here will end up being E. Okay, after we execute the C instruction. And so the algorithm for this stack, what do you think will happen when the next PC equals the reconvergence PC? What do you think that stack should do? Pop that entry off. Okay, so the operation is, as soon as I see reconvergence equal next PC, I pop the entry off. That means that I'm done with this path because now it's supposed to reconverge with something else that's running. Okay, and you'll notice that when we performed this divergence, we also updated the next PC of the first entry to be the reconvergence. So that way, once we pop everything off, we know everyone's good to go at E. That's how this is going to work. We will continually push entries onto the stack as we split, and then we will pop them off as we reach the reconvergence points. Okay. So we do this execution of C, and then it will end up being the EPC, which will cause it to be popped off of the stack. So then we will select whatever is the top of the stack now, which happens to be the other path, which we deprioritized. In that case, we were going down the active mask looked like this. So we will execute that instruction with 50% execution efficiency. And then it will also equal E after it's executed D. The next PC here will equal E. So then we'll pop that entry off as well. And then we're back to the very top of the stack where we just have one entry and everyone's happy again. Because we're all going to execute E together. Then we'll all execute G together. And then, potentially go back and do A and start the whole thing all over again. Okay. And so in this way, you can create this very efficient hardware mechanism to track. A stack is a very natural fit for this, right? You sort of are splitting and then reconverging. So pushing and popping things off a stack really is a good data structure to use for such an exercise. You can build hardware stacks, in silicon pretty efficiently. And that's how the GPU keeps track of how the threads sort of move and diverge as control flow instructions are executed. Okay, yeah.
What happens when you have like registers that are being used in both branches, but you're executing each?
Yeah, good question. So if, for example, like I have two paths here. Okay, I have C and D, and let's say that they both write to register R1. That means that when I come back together, I actually will want different things in R1, right? That's what the code would have said for each of the two different paths. So when I execute the instruction, the C instruction that writes to R1, I execute it with this active mask, meaning that those middle lanes will not perform a write to the register file. So if I'm writing to R1, I'm really only writing to R1 in the side, basically the bookend lanes. And then when I go do the other side, I'm really only writing to R1 in the middle lanes. And then when I come back, if that was really what the code wanted to do, then I've executed maybe a subtract on R1 on those two lanes and then add an R1 in the other two lanes. But that's actually what we wanted in R1 when we came back together. Okay, so that's absolutely possible, but it just depends on, it just sort of elegantly handles what the scalar code really wanted to happen between each thread. Does that make sense?
Yeah.
Yeah, good question. Other question, yeah.
Since it's about where's the, don't you only have a finite amount of diagrams?
Yep. So you can compute what the maximum size of the stack could be based on, all of the threads going off in the weeds in any potential way. Like it's capped, right? It's capped by your warp size. And it really just, there is an equation for this. I think we have an equation for it in the book, but it's wrong. We have a better equation for it. I can actually post that to Piazza, but it's calculatable how many entries you could have at most if you've got a 32 size board or a 64 size board, for example. And it's not just, like the worst case is everyone goes in their own direction, right? So there's 31 different unique paths, or 32 different unique paths. But, you have to have, every time they split, you have to have a new entry for that sort of split place. So it's actually more than just 32. It depends on, but you can calculate this. Okay, good question. Yep.
Does this mean you can optimize your code by making sure you reconverge as soon and as fast as possible?
Yeah, so the compiler actually plays a very prominent role in how it lays out the code here. And we can see that the compiler can actually, it can screw it up if it lays out the control flow in a strange way. So GPU compilers are a special kind of hell. And that's a direct quote from somebody at NVIDIA that works in GPU compilers. Because they have to manage this kind of thing, and they also have to manage concurrency, right? Because if I use too many registers, then there's not enough, I'm going to hurt occupancy of the other warps. So you have these other dimensions that you have to handle when you're trying to compile GPU programs. And based on the way that the compiler takes the C code and creates the control flow graph, it can create one that's better or worse for this type of thing. Generally, if it does the normal thing, right? It does what a normal CPU compiler would do, and then just sort of handles it. There are some perverse cases where, this will actually break MIMD functionality, which we'll talk about not today, probably next week. Okay. Other questions here? Yeah.
The reconversion, is it reconverge to the active mask after the split, or all the big?
It will be the active mask at the point of splitting. So in this trivial example, your active mask was full, but it was possible that somebody went down F, and then I only had 3 warps or 3 threads active when I split at B, which means when I come back at E, I will have only 3 left. So it's recursive, right? So every time you split, You're only splitting whatever is left and they're only reconverging whatever is left. Good question. Yeah.
If we switch ones in between C and D, will the stack, how do we save the stack in that case?
So this is persistent, yes. So this is the cost that the hardware pays to basically implement the SIMT front end. So you need discrete, different hardware stacks for every warp that is executing on your core. And you need as many entries as you need the maximal number of entries to make sure that you don't overflow. And that's just the cost of the SIMT front end. Okay, good question. Other questions? So yeah, every warp has its own SIMT stack. There's no sharing here. They're completely independent. Okay, no other questions? This is pretty fundamental, right? This is really part of what differentiates GPUs from vector machines is this sort of SIMT front end and this convergence and this divergence and reconvergence mechanism. Okay, and this is modeled in the simulation infrastructure. Okay, so how did this get implemented in practice? So like I said, the compiler will implement special push and pop instructions that it puts at the split points and the reconvergence points. So it has to figure out where the reconvergence points are. So it may not, depending on the implementation, like in my simple example, conceptually, the PC has to be the same as the reconvergence PC. If you already know in the compiler where you're going to reconverge, you just put a pop instruction in there. And then when it gets there, it'll pop it off of the SIMT stack. And if you look at the NVIDIA and the AMD ISAs, that's really how they usually do this. You can also use predication. So if you don't have recursion, you could basically keep track of this SIMT stack in software. Right, there's no reason why I couldn't compute this stack in software, and then I couldn't apply the mask at the top of the stack as the predicate to every instruction. So you don't necessarily have to have a dedicated piece of hardware. You could do this entirely in software, with special instructions. And AMD machines did this at least for a long time. They had a special scalar unit that would do all these computations. To sort of basically perform the operation of the SIMT stack and then just predicate all the vector operations with whatever was at the top of that software stack. So it doesn't have to be in hardware. Historically, in NVIDIA machines, it has been in hardware, and in AMD machines, it's been in software. Okay. All right. So there's some quizzes online about some of this stuff. Actually, I'm over time. Any questions on this before I let you go for the day? All right, good. I'm excited to move into the hardware part of the class. Do read those papers, please. The cuDNN paper that I posted online. It's pretty relevant, especially in today's world. And I'll see you guys on Thursday. Okay? Thank you.